Okay, let's do another separation of variables problem. This will be an initial value problem. So we're going to actually solve for C and get a particular solution here. So I claim this is a separable DE. It's possible to get all the y's onto the left side and all the x's, including the dx, over to the right. So first, I would want, remember, you're always multiplying or dividing stuff to move it around. Don't add this xy to the other side. That's not going to do you any good, at least not in this case. So let's factor a y out here. Okay, so now I got to figure out how to get this y to the left side, this x squared, and this dx to the right side. So I can divide the y over and do 1 over y dy equals, to get the x squared to the other side, bring it to the bottom, and bring this dx up to the top. Remember, differentials aren't actually algebraic quantities. We really can't multiply them over. But it turns out mathematically we can pretend we can and we still get the right answer. Now we just integrate both sides. So I want the antiderivative of 1 over y dy. We're really integrating with respect to x, but because of chain rule, we end up doing antiderivative of 1 over y dy. We integrate with respect to y on the left and with respect to x on the right. I'm going to split this up. 1 minus x over x squared would be 1 over x squared minus 1 over x. It'll be easier to integrate. Antiderivative of 1 over y is natural log of the absolute value of y. Antiderivative of 1 over x squared is negative 1 over x minus, and then we get a natural log of x plus c. And then we could rewrite this in exponential form if we wanted to get an implicit or an explicit solution. So I could say, just make both sides, entire sides, powers of y, or of e. And again, we're going to drop that absolute value. We get two branches here, but we're going to assume the positive branch. Say y is e raised to all of this stuff. Remember, in an exponent, a bunch of things added together could be multiplied. So I could say this is e to the 1, negative 1 over x, times e to the negative x, negative natural log of x, absolute value of x, times e to the c. I can absorb all that together and call that one constant. This negative here, it's times, could come up as an exponent and make that 1 over x. E raised to the ln of 1 over absolute value of x would just be absolute value of x. E to the c, I'm just going to call some new c. And so I end up with this. Okay, now I'm going to solve the initial value condition. Net y of negative 1 equals y of negative 1 equals negative 1. So plug in a negative 1 for x, and my answer, y, should be negative 1. So negative 1 equals c, e to the negative 1 over 1 over absolute value of negative 1. E to the negative 1 is just 1 over e. So I get negative 1 equals c over e. So c equals negative e. Absolute value of negative 1 is 1, of course. So our final solution will be negative e to the negative 1 over x over absolute value of x. Now, if we had used the implicit version right here, to solve our initial value problem, we would have gotten a different value for C. This C and that C are not the same. But that's no big deal. We could do it, and then if we try to convert that into explicit form, we would still get the final solution. That final answer would still be the same. So it doesn't matter that we've changed what we meant by C here, our constant of integration. What matters is we don't want to solve this for the initial value problem. Think we got C and then use that value down here.